Random variable. Something that can be measured, can take on any range of values. So when we flip a coin, it could be randomly heads or it could be randomly tails. Discrete random variable. Some things can only take on a list of possibilities. I can't get heads, tails, and something else. Right? So if I flip the coin 3 times, I can't get heads 5 times. That just doesn't happen. I could get heads 3 times. I could get heads 2 times. I could get heads once, or I could not get heads at all. Those would be the possibility, but we have a list that is finite, countable, and that's all that we can get. So, if I roll a dice 4 times, here's my dice, the number of 3s that you could get. Is it possible to get 0 3s? Yes. Is it possible to get all 4 3s? Yes. So you could get, let x equal the number of 3s, you could get 0, you could get 1, you could get 2, you could get 3, you could get 4. There would be 5 possibilities of what could happen if I was counting how many 3s I got when I rolled 4 times. A continuous random variable is when you have all options available. So if you were trying to guess how long it took for a car to finish a race, since there's milliseconds, there's any possibility of times in between. It's not like the car traveled in seconds and it just hopped forward like that and there was no milliseconds involved. And a probability distribution that we're going to look at for the discrete ones is a list of each possibility and the chances of that possibility happening. Oh, fun, fun, fun. Okay. I like probability more than statistics, although they're very connected, but I think we get more fun problems in this. So, flipping a coin twice. It's pretty straightforward. You could get heads or tails, and then heads or tails, heads or tails. And if I was writing out the possibilities, this would be the sample space. There's 4 things that could happen. And when a question says a fair coin, that means that it's perfectly 50-50 and considered fair. It's not a coin you found at a local fair. You're like, ooh, I was at the Red River X and I found a coin. And this becomes a, no. So it just means that it's a 50-50 chance. So we can make what's called a probability distribution for this. We define our variable x as the number of heads you could get. And if we look at our sample space, you could get 0 heads, 1 head, or 2 heads. The chance of getting 0 heads was both tails. That happened 1 out of 4 times. 1 head happened 2 out of the 4 times. And 2 heads happened 1 out of the 4 times. Usually there's a little x there. Notation-wise, if we define x to be 0 heads, 1 head, or 2 heads, what this part is saying is find the probability of there being 0 heads. Find the probability of there being 1 head. And the notation, they say x equal to 0, x equal to 1, x equal to 2. And it will always be in a probability distribution that if you sum up this row, it will equal to 1 because it's 100% of all possibilities. Now this is a very easy concept written in very confusing math language. Okay? This part here is telling you exactly what I pointed the arrow to in the last one. When you add up all of the probabilities, you're going to get 1. How do we write that mathematically? That's the symbol for the sum. If you add up all the probabilities, you will get 1. This part says that each probability on its own has to be between 0 and 1. That should make sense. You'd be like, oh, my chances of flipping a coin are 130% to getting heads. It doesn't make sense. You can't have a value higher than 100%. You can't have a number less than 0, right? But you've probably heard people say there's a less than 0 chance that that's going to happen. So that's some good math. So if you toss a coin 3 times, you can make a tree diagram for that. And then I want you to fill out the probability distribution chart. So if X is the number of heads, you could get 0, 1, 2, or 3. Then you put the probability on the bottom. Okay. Looks like most people are close to getting their chart done. If you're struggling with the chart, I will color code it here. I think will help you see what's happening. Okay? Now, if X is the number of heads, you could get 0 heads, 1 head, 2 heads, or 3 heads. And that's the only one with 0 heads. There's 8 in total, so this becomes 1/8. 1 head, there is 1 here, 1 here, 1 here. 3 out of 8. 2 heads, there'd be 1 here, 1 here, 1 here. Also 3 out of 8. And all 3 heads, 1 out of 8. So you can see how the sample space tells you your answers, and I hope my color coding really made it obvious where they came from. without drawing our tree diagram. We're going to flip that coin one more time. If we flipped it one more time, would you agree Would you agree the possibilities of getting heads would be 0, 1, 2, 3, 4? Okay. If you flipped it another time, can you see that these fractions would be over 16? Because you have 2 times 2 times 2 is 8 times 2 is 16. And would you agree that these ones would have to be 1s? Now, without counting them, I'm just going to put these numbers in here and have you enjoy them. That's what would happen if there were 4. And why are those numbers enjoyable? Pascal's triangle. Did you see that we had 1, 3, 3, 1 in the previous one? And in the first one, it was 1, 2, 1. And if you did the coin flip 5 times, you would get 1, 5, 10, 10, 5, 1. So interesting. Okay, well. A box contains 2 red marbles and 6 green marbles. Two marbles are chosen at random with replacement is important. So once you pull out a marble, you look at its color, then you put it back in, then you pull out a second marble. And X is the number of green marbles obtained. We can draw a tree diagram for this. And in this case, unlike the last one, when I do red and green, I might also add that getting the red one is 2 out of 8, the green one 6 out of 8. And then red again and green, 2 out of 8, 6 out of 8. Red and green, 2 out of 8, 6 out of 8. So we can write the probabilities on the branch, and since there's replacement, the probabilities stay the same. And this would be red, 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 green, green, red, green, green. So if we want to do a table here, and X is the number of green marbles that you could get 0 green marbles, 1 green marble, or 2 green marbles. Your probability of 0 green marbles is going to be 4 out of 64. Yes, I could reduce that, but for right now, I'd like to keep it as 4 out of 64. Next one that's easy to do is the green, green one. Can you see that that one is 36 out of 64? And then red and green will be 12 out of 64 plus 12 out of 64. 24 out of 64. And the reason I wanted to keep them all out of 64, even though I knew I could reduce them, I think it's really easy to see if they're all out of 64 when adding them up, that it still adds up to 1. I mean, this could have been reduced to 1 out of 16. This one could be 6 out of 16. And this one, 9 out of 16. That would work as well to still see that it adds up to 1. But I kept them as their full fractions in this case. This is kind of a different way of looking at things. This would be an interesting way to play Monopoly. So you roll 2 dice, and you want to subtract them. Oh, I rolled a 1. You could roll a 1. You could roll 0. Oh, it sucked, eh? You land on boardwalk, you have to pay the other person for hotels, and the next time you roll doubles and you get a 0, so you stay on the same spot and have to pay again. But if we draw out the sample space, does this make sense? Anytime you get doubles, you get 0. This would make a very slow Monopoly game because the most you can move forward is 5. And you would probably hit almost every single spot on the board in a couple of times around. So then it's just a matter of, can we figure out each of those probabilities from the chart? They're all out of 36 because there's 36 in total. Good. Is this valid? Yes or no? And why? Could this be possible? Now, why are you saying you're shaking your head? It adds up to more than 1. So it would have to add up to 1 to be possible. This one doesn't. Okay, we'll do one more together, and then I want you to try 9 and 10 on your own. And if you want, you can go up to a board and do it on the board rather than your notes. It's up to you. So sometimes you get a question like this that's abstract. Consider a random variable x. Probability of happening at 0 is a. Probability of happening at 1 is 2a. 2 is 3a. You could draw a probability distribution chart for this. Once you draw your probability distribution chart, you're like, oh, I think I see how I would solve this now. All of the probabilities have to add to 1. So if you added these 3 up, you'd get that 6a has to equal 1, and then a would have to be 1/6. So we're going to find, for these questions, drawing this distribution chart is going to be helpful for us, and we're going to find it's a way of organizing our data. So examples 9 and 10. are going to ask you to draw this chart. You might want a tree diagram to see the probabilities. That's perfectly fine. Whoops, almost gave it away. So, thought I had the orange box. Try question 9 and 10. I'll put up number 9. You can check if you're doing it right. All right, I'll put up the answer for number 10 as well.